Hi, I'm Dhruv.
And I'm Arun. And we are fourth year electrical students from Manipal Institute of Technology.
PCBs are becoming more and more complex, and their component density is on the rise, making manual visual inspection a tough, tedious, and time-consuming process. To take care of that, we designed an automated PCB verification system. In this system, we use image processing algorithms to find components missing and components present on a PCB. We built a two-axis motion platform for the camera. It uses two motors, one for the x-axis and one for the y-axis. This platform gives us three distinct advantages. 1. By taking multiple cross-sectional images, parallax can be eliminated. 2. PCBs larger than the field of view of the camera can be analyzed. And 3. Multiple small PCBs can be analyzed in a single cycle. The heart of our system is the Beagle Bone Black. It's a powerful Linux computer with an ARM A8 processor running at 1 GHz. The image processing is performed on the Beagle Bone Black, and it also controls the stepper motors. This is our stepper motor. It has a step angle of 1.8 degrees and provides a torque of 0.5 Nm at a current of 1.7 amps. Here is our stepper motor controller PCB. There are two such PCBs, one for each motor. Each PCB has a single DRV8811 stepper motor driving IC. They are supplied with 12 volts of input power and 5 volts of VCC from the 7805. The 5 volts is also used to supply the Beagle Bone Black with power. We have provided extensive heat sinking to prevent the IC from reaching thermal breakdown. A zero PCB has also been provided for expansion. We are using an off-the-shelf webcam, the Logitech QuickCam Pro 9000, to acquire the images. The camera starts moving from the home position to the test PCB and takes its snapshot. The motors are being driven in a 1/16 microstepping mode to ensure smooth operation. These motors rotate the threaded rods, and the nuts on them are mated with the linear bearings, which moves the camera in case of the x-axis motor and the x carriage in case of the y-axis motor. The camera then moves to the reference PCB and takes a snapshot of that. After taking both snapshots, the camera returns to the home position while the Beagle Bone processes the images. For our first demo, we are using a hard cascade classifier to identify the LEDs and compare the two PCBs. This is a raw image from the camera. We use edge detection to find the bounding rectangle and crop the image to get the PCB. The hard cascade classifier then identifies the LEDs and highlights the area where they might be missing on the test PCB. For our second demo, we will identify the missing components in a burnt stepper motor controller PCB with the final stepper motor controller PCB as the reference. After cropping the image, it is converted to the HSV color space, that is hue, saturation, and value. We apply a thresholding filter to get a binary image. You can clearly see the resistors over here. To remove the noise, we use a combination of a bilateral filter and morphological operations to get the final image shown on the screen. The process is repeated to get capacitors and ICs. Here is what the final output looks like. The components are color-coded with the centroids marked. This is then compared against the objects in the reference PCB, and only the missing components are highlighted as shown on the screen.